Hello and welcome to a video tutorial for the 2008 mechanics paper. Question 1. Louise is playing soccer for her first 11 soccer team. Louise has a mass of 65 kilograms. Louise is running towards the goal at 8 meters per second. She slows down to 6 meters per second in 3 seconds. Calculate the distance she travels over the 3 seconds and write your answer to the correct number of significant figures. Right, so we need to find the distance, and we have the initial velocity, the final velocity, and the time. So we need to find a kinematic equation here, which has distance, velocity, initial velocity, final, and time. So this one here. So D is equal to VI plus VF all over 2 times time, which is equal to 8 plus 6 all over 2 times 3. So that's just 14 over 2 times 3, which is 7 times 3, which is equal to 21 meters. But we need to give it to the correct number of significant figures, and these are given to 1, so ours needs to be given to 1, which is 20.0, well, you don't need to do that, meters 1 SF. State the main energy change when she is decelerating. So her kinetic energy is decreasing. Obviously she's moving, so we have kinetic energy to start with, and that's decreasing because her velocity is decreasing. But what's it changing into? Well, if she's decelerating, then essentially more of her body power is going into the ground, causing more friction, more heat and sound. So kinetic energy, well, it's not exactly more friction, but it's more prominent, I suppose. It's causing heat and sound either way. Right. Calculate her kinetic energy while she is running at 8 meters per second. So if we bring the formula sheet back, where's kinetic energy? EK is equal to half of mass times velocity squared. And we know her mass is equal to 65 kilograms. And the velocity is 8 meters per second. Oops. So that means that this is equal to half of 65 times 8 squared is 64, I think. So 0.5 times 65 times 64 is equal to 2080. And this is in joules. Okay, so calculate the size of Louise's momentum while she's running at 8 meters per second. So momentum's very similar to kinetic energy in a way. P equals mv. As you can see, the formulas are kind of similar. So this should give us, it's not really telling us the same information as the kinetic energy, but it's basically telling us how much oomph she has when she's running, what's going to happen if she stops. So P is equal to mv, which is equal to 8 times 65, which is 520. Now the units here are important because we've got the mass, which is in kilograms, and the velocity, which is in meters per second, and the units for momentum is basically the product of these two units here. So this is going to be kg ms negative 1. So if the speed was given in kilometers an hour, then this would be kmh instead of ms. But it's not too difficult, really. while she's running at 6 meters per second to the right, the ball rolls at 4 meters to the left. So we've got Louise rolling at, moving at 6 meters to the right, and the ball is rolling 4 meters to the left. So the relative velocity here is basically going to be these two vectors combined, which is going to be 10 meters per second. And that makes kind of sense when you think about it, because if the ball's rolling that way, you're running this way, the relative velocity is going to be higher than both of them, and it is actually both of them combined. Determine the size of the average net force acting on her when she is running at a constant speed. So this is interesting because obviously if she's running at a constant speed and the net force is 0, we have here F net is equal to ma. Where's that? Here. So we know that Louise has mass, obviously. Oh, can you see what I'm writing on? We know she has mass, so if there's any net force, then that means there has to be acceleration. But if she's moving at a constant speed, then there is no acceleration. So as Louise is moving at a constant speed, the net forces, or the net force acting on her is 0. We can just say the forces are balanced. Or the forces must be balanced for constant speed. With no acceleration, I guess. Yeah. Right, Louise kicks the balls vertically up, shown in the diagram. Oh, I drew on some of these earlier. It rises and then falls. You may assume the air resistance is negligible. So, as we can see here, the only force that's actually acting on the ball is gravity, because when the ball is being kicked, there's obviously a huge force coming from the foot. But the force isn't, the foot isn't in contact with the ball anymore, so there's no way that this is actually acting on the ball. The only thing that's acting on it is gravity. That's in the air, nothing touching it. So it's moving down. Essentially the only force is the net force, which is gravity, pulling it downwards. And obviously gravity is pulling it downwards. And gravity is constant. So what's this doing to the acceleration? Well, it's constantly accelerating downwards. Obviously, we have this here. Net force equals to mass times acceleration. So it's constantly accelerating downwards. But on the journey downwards, it is actually accelerating downwards. It's increasing the velocity here, whereas here it's decreasing the velocity. It's still going downwards, but we can't say it's constantly decelerating, because although it's true on the way up, it is decelerating the ball until it reaches its peak. It is actually accelerating it downwards. So instead of just saying it's decelerating, we can say it's constantly accelerating downwards. One thing which is very important to note is at the peak here, there's no acceleration because there's essentially no velocity, which we'll come to in a second. It's just momentary, but obviously it gets to the point where the velocity reaches 0 and then it starts heading down again. So the ball is constantly decelerating downwards, but is momentarily but there is momentarily no acceleration. At the top, I guess we can just say that. Velocity. So the velocity is upwards, but constantly decreasing when it's rising.
Sorry for the interruption. Can Chinwei Chatuta please come to the section now? Thank you.
I don't know if you could hear that, but that was quite loud. When the ball is rising, there, the velocity is 0 at the top. Momentarily. And then downwards. And increasing. On the way down. Although that's kind of self-explanatory. Another thing which we can say is that this is projectile motion, and we know that I don't know if you can see what I've been writing. The camera doesn't cover very much. We know that the initial velocity is equal to the final velocity as the ball goes up and down. So we can talk about that as well, I suppose. So you don't really need to say that, but it doesn't really hurt. And it is true, so you can add that in as well. I probably went over the limit a bit. My handwriting's terrible. So, a while later, the ball is rolling towards Louise at a speed of 8 meters per second, as shown in the diagram, right? She kicks it and it rolls in the opposite direction with a speed of 12 meters per second. The ball's mass is 450 grams, and her foot is in contact with the ball for 10 seconds. So we need to calculate the size of the unbalanced force on the ball. So essentially, we need to find the net force. And we have an equation for that, or a formula. F equals ma. So the force is going to be equal to the mass times the acceleration of the ball. And we have the mass of the ball here, 450 grams. So the mass is equal to, and that's 0.45 kilograms. It's important to change that, otherwise you'll get a very different answer. So we need to find what the acceleration is. acceleration is equal to, well, we can't just rearrange this. We know that acceleration is equal to the change in velocity over the change in time, and that seems like it's going to be useful here. So we have the initial speed here, or, well, I'll just write this down first. So we need to find the change in velocity, so it's rolling towards her at 8, and then it leaves at 12, but these are in different directions, so again, we have 8 that way, oops, 12 that way, so 8 plus 12 is 20, so it's really, if you just need to draw vectors and add the vectors, and you'll see that the velocity, the change in velocity is 20 when you include the changes in distance. Otherwise it would just be 4, so it's important to remember this. And the change in time, oops, change in velocity, the change in time is equal to 0.1 seconds. So if we do that here, A is equal to 20 over 0.1. I don't know if you can see that, which is equal to 200. So F is equal to 0.45 times 200, which is equal to 90 newtons. State the size and direction of the force. State the size and direction of the force of the ball on her foot. So, with, I think it's Newton's first law, Newton's second law, every force has, or every action has a reaction, and they're equal sizes, equal everything, or opposite directions, I suppose. So the size is going to be the same here. The ball exerts the same force on her foot as she exerts on the ball, so it's going to be 90 newtons, and it's going to be to the left, just the distance the ball was rolling before, or the opposite of the direction it was rolling afterwards. Basically, the foot is acting that way, the ball is acting that way, so those are supposed to be the same size because they're equal. So it's going to be to the left. And going on to question 2, and I think I'll stop the video here and do the next one in a separate video because we've been going for 18 minutes. See you soon.